Hey, so good evening, good morning, whatever it is for you. Uh, Today I'm going to go over reinforce, which is an algorithm used in reinforcement learning. But this video mostly serves as an intro to um, the use of RL in LLMs, and I'll go more into like my inspiration, my motivations into kind of exploring post-training and how reasoning is applied to LLMs. But essentially, this video will serve as a little segue into it to kind of understand how these algorithms work and try to build a mental model of this. And from there, we will dive deeper this summer into more complex algorithms and approaches to enabling reasoning in LLMs and making them smarter, sound more human, and basically the whole pipeline after we have a pre-trained model. And what served as inspiration for this was, let me share my screen. Let's see. Yeah. So what served as inspiration for this was earlier this year, well, a month ago, after I did the lecture on GPT-2, building it in JAX, and the whole lecture on transformers and attention, and basically building that understanding of how the technology that revolutionized the world actually works, I did this lecture on post-training an LLM. Now, to me, back then, that was a kind of like a chill session before entering the final week, which is where I worked on diffusion. This was for the AI Guild. But as I was kind of researching the topic more and moving past the vocabulary of, or like the buzzword of RLHF and things like that, it kind of just opened this huge world into post-training. And post-training is this immense topic and something that I find very interesting and very important into the future of AI. And I'm going to briefly explain kind of what RL is, and how it's applied to to an LLM. First, I'm going to go over kind of the pipeline that I talked about in that lecture. So dragging this here, let's put this in slide mode, and let's see what any of this even means. So just the whole point of RLHF, reinforcement learning from human feedback, is to push our model, our pre-trained model, which is very intelligent and can generate text, into a more conversational being. And obviously, we talked about supervised fine-tuning. You know, that's kind of how you get it to respond to prompts. But that is a very expensive and low data way of approaching this. And so a more efficient way is to just, in a chat, and probably you guys have had some experience with this in a way, you ask ChatGPT something, you ask Gemini something, you ask Claude something, and sometimes they give you multiple responses, and you're supposed to pick, I prefer this response, I prefer that response. That serves as a much more efficient way of explaining to our LLM what a response is supposed to be like. Instead of giving it, here is the perfect response for this question, which is what supervised fine-tuning doesn't actually. I should have something about it here, right? We kind of have a perfect response written by a human, and then we feed it to the LLM. We fine-tune it off this data set of prompts and golden responses. Instead of going by that approach, we have to realize a lot of responses to questions are very like have a lot of different correct responses. You know, if I ask someone, how do you, just a very subjective question, deal with how do you deal with pressure when you're under a lot of pressure? How do you deal with it? What's the right answer? You know, there's a genre, like a cloud of a right answer, right? How do you deal with pressure? I don't know. Some people say meditate. Other people say, relaxation techniques. Others say go under more pressure, and in that way you get more accustomed to that environment. And they all have these different perspectives, but it shows you that there's no golden answer. That's another reason as to why we need RLHF, in that this kind of generalizes to human preference, especially for questions that don't have a golden response. And so RLHF, what we do is we have a bunch of responses generated by the model to a certain prompt. And I'll show this here. This is a little cute diagram thing I made. We have a policy model. What we define as the policy model is, just think of it as the pre-trained model. So the big brain pre-trained GPT-2 model, fed it a bunch of data, did a little bit of fine-tuning on it, but now we want to further that process. That's what this policy model is. And then the reward model is, if you have ever read, for example, the CLIP paper, what they do with some of the ResNet models is, if you think about it, maybe I should draw this out. Nah, let's just talk about it, right? You have this model, the ResNet model. It's CNN. Actually, let's search this up and let's be more clear about this, just to have like a grounded idea of what we do. Let's see if I can find it. But there's something called linear probing. If you think about what the ResNet model does, it classifies images under a data set. And so we have to have our output layer be the same amount of dimensions as the amount of labels that we have in the data set. So for example, if we have a data set of 1,000 labels, we need an output layer of 1,000 neurons. Now, I'm trying to find here where they talk about linear probing. But basically what linear probing does is that we basically lobotomize that last layer. We completely take it out, and then we leave the second to last layer, which is, in the case of ResNet is 2048, whatever. And then what we do is we replace that output layer with whatever number of labels are in our new data set that we're testing on. So if ResNet was trained on ImageNet, which I believe is 1,000 labels, what we get is the model, output layer is 1,000. We take off that output layer, and then let's say we want to test on a data set that has, that just differentiates between a cat and a dog. 2 examples. So our output layer has to be 2 neurons, right? And what we just do is we put a custom layer of 2 neurons for that output layer. Hope that makes sense. Why is this important here? Our reward model is literally a copy of our policy model, except we take that last layer. And if you think about what a transformer is, the final layer is of size, vocab size. Like the size of your vocabulary, that is the output of our transformer. Why? Because, again, we're predicting the next token given the past tokens. When we predict a next token, we have to have a probability distribution throughout all possible tokens in our vocabulary, highest probability, or we sample from that. What we do is we take that final layer out, and then we have a singular scalar value as our output. That is basically what this reward model is. And what we train this reward model to do is it grades, it naturally grades given our rankings of things. So remember, you're given two options. Let's say in your ChatGPT chat log, you're given two options. You press I prefer this option. That one is ranked higher than the other one. This is fed into the reward model. And the reward model basically learns the structure of a good response relative to a prompt compared to the bad structure of a response. And this looks kind of like this. Well, once we train this model, what happens is we now are able to feed a prompt to our policy model, right? And it gives us a response. Now, normally, in this case, I put what is a crocodile as a prompt, and the model responds, crocodiles are monsters that eat people alive. Not true, not fully true. So this, you can consider it, maybe it's a like a real response. Sure, some perspectives may see that, but it is not the most, it isn't just not the best response. And I think we can all agree on that. And so if we treat the prompt as an X and a Y, we feed this pair as input into our reward model. And as I said before, our reward model now outputs a scalar value. In this case, -4. This would mean bad, like, yo, don't do that again, straight up. And then through training in RLHF, what we have is now a trained model where the response is fitting for the prompt. And when we feed this to a reward model, it gives a good reward. But let's talk about the actual intricacy of this. I believe RLHF, this whole process is very intuitive and very simple to understand and build an idea of. But we have to pinpoint a couple things. And to do that, I'm going to stop sharing my screen here. And how do I do that? Where's my Google Meets? Oh. Okay. I'm going to share my iPad so I could actually like draw stuff out. What is intricate about this? What is difficult about this? Again, remember, our goal is to understand and have an actual idea of how post-training works. Let's kind of keep that idea in mind. Let's hold this. Let's hold the thought of RLHF. And let's think about what supervised learning is. Fundamentally, supervised learning is, in the context of a transformer, let's make it really simple. We have a sentence, right? We have a sentence, the car is blank. No. We have a sentence, the car is green. Let's give it a color. This is the ground truth. Our model so far has outputted. So this is ground truth. The model has outputted the car is blank, right? It's trying to predict this next token. And let's say it predicts it's like totaled. In supervised learning, the way we rank, the way we grade a model's response is very simple because we have a ground truth. And so our model outputs the car is totaled. So for it to output the car is totaled, it has some distribution across the vocabulary size, right? So maybe it, 9% thought the car was green, and then 14% it thought like wrecked, which is synonymous with totaled, but then 27% put totaled, and that's why I picked totaled. But the truth is, in this case, the ground truth is that it is 100% green and 0% this and 0% rect and totaled. And so what we do is we kind of compare this distribution. We kind of compare the distance that our distribution here was from the truth. And mathematically, we give it some grade. That's what we call our loss function. And our goal is to minimize this loss. Second. Our goal is to minimize this loss. But it's really easy, right? There is a ground truth. Think about what we were talking before. In human preference, there is subjective truth, but it's hard to reach an objective truth. Like what we talked about, the crocodile question. Someone can say reptile in tropics. Other one can say, reptile, but something else. Reptile, maybe go into their taxonomy, so then they're more like specific. I don't know if this is true or not, but I don't know, crocodilia, right? They talk about something in that genre. One explains it more simply, the other one explains it more higher, lower level, but both are correct. So this is a very noisy environment to create a loss function for. And so what we do, this is why we trace back to reinforcement learning. Oh, and one more thing. If you remember, here we have, I believe I made it red, so I'm going to have it here. Outputs a number. This is our reward model. And then we have our policy outputs, given a prompt, it outputs a Y. And then given an X and Y, it outputs a value that ranks the Y response of this. We have to find a way to create this random, to have this random reward, which is what we call it. We call this a reward. We have this random number. It's not ground truth. It's just a grade for what we outputted with this model. And we have to find a way to grade this. Now, the goal overall is the opposite of the loss, actually. Our goal is to have our reward and increase the reward. But how do we attach this number to this model in a way that this model's weights through backpropagation learn how much to update their weights given this reward? It's actually surprisingly, or not surprisingly, but when you look at it in that sense, you can kind of see why the need for a more, or why it is a very complex problem that we actively focus on a lot in the AI space. And so we have our reward. We are given some reward by a model, reward model, outputs 15, or in this case, just imagine our reward is 15. How do we convert this into signal? How do we convert this 15 into signal for our, neural network, whatever, to perform backpropagation correctly, right, and update the weights? Normally, what we do is we have this loss. This loss signals to the parameters of our model to nudge, in specific directions based on the gradient so that our loss goes down. In this case, we have to do the same with a reward, but the reward, again, is very noisy, and it depends heavily on the environment and on the action we took, things like that. Well, in this instance, this actually falls very much in line with what reinforcement learning is. And so let's talk about reinforcement learning. Reinforcement learning is separate from what I talked about here, supervised learning, in which we have an agent, what we call an agent. I'm going to use a more classical example of RL, kind of separate it from the neural network right now, and then we're going to re-implement it into our neural network. And so, for example, reinforcement learning, in reinforcement learning, let's use the example that we are going to build on. It's a very classical beginner example. And it's called cart pole. We are given this little cart with wheels. It moves left and right. It has a stick on top. But this stick is like very wobbly, so it starts like falling over. Our goal is to move this cart left and right, such as we can keep the stick on the cart as long as possible, or as long as the turn is. And let's call our cart like the agent, or let's have some model represent the agent. We have to find out what movement given a specific state. So for example, we are given this part, but then the pole is falling this way. Now let's think about physics a little bit. We move this way, it's more likely to stand up. And it's not loose, there's like a little hinge here, right? So it's just falling over. If we move the cart to the right, we know that off physics, we know that this is gonna stabilize. Because if we move this way, this thing's just gonna fall forward. Hopefully you guys can visualize that. Well, how do we teach a model to learn this? The thing is, we are given a state. So imagine this is a state, this is a state, this is a state. We have a state, and our inputs would be like the situation at hand. So for example, in this case, we have how many degrees in this direction it's moving. There are other things like angular velocity, velocity period, things like that. I can't remember it off the top of my head in this example, but that is kind of a descriptor of our environment. So think about how we can plug this into some neural network. Let's say we have 4 descriptors. That's what we have in cartpole. I don't remember exactly what the numbers are, but we have 4 numbers. And given those 4 numbers, we have to make a decision. Do we move left or do we move right? This is our 4 inputs and then our 2 outputs, left or right. And now, given our decision, which we call an action in reinforcement learning, let's say we move left in this instance, the environment that we're in will give us some reward. So again, think about this scenario. If we move left here, this thing topples over. The goal is to keep this straight up. So if it toppled over, we kind of did a bad turn. That is a bad action. The model or the environment will give us a bad reward. Again, try to connect all of these concepts back to RLHF. We have a reward model that gives us a bad reward for a bad action and a good reward for a good action. So this topples over, boom, we have a reward. And then let's say whatever that reward is, let's say it's 0 because it toppled over or something. We have to convert this into a signal to pass through our neural network so that its weights update through backpropagation. And there are many different, I'm going to create like a little visual, but there's a lot more complex math and especially probability talk around reinforcement learning, and we will go more in depth into this as time goes on. But for now, kind of keep this intuition in mind, right? And basically what you have to keep in mind straight up is that we have a box. This is our environment in reinforcement learning, where we are given a state and we are given a reward. And so, here we have our state, here we have our reward. This goes into our agent. Now, what we will be working on is policy-based, and we'll talk about that more. But when you think of a policy, if you guys saw back in the slides, this model, where are we at? Damn. This model is what we call the policy model. So what we are grading is the policy, the output of our policy. This is just a policy. The policy, it's usually denoted by the pi. By pi, it is the probability that an action is taken given a specific state. And then this action is applied to our environment, which then updates to the next state. It's given a reward and all that. Let's like grapple back into how this applies to our reinforcement learning from human feedback, how this applies for LLMs. We have our policy. This is the same as our LLM. Let's think about this in a reinforcement learning context. We have our input. The tokens are the input. Well, we have input. So let's say the prompt. The prompt is our current state. And this produces an output. In this case, the output was our answer to the prompt. And this is our action given the state. So again, the state is equivalent to the prompt, and the action is equivalent to the generated response. And our reward in this instance is the score that our reward model gives, and that in this instance is part of the environment. The score reward model gives to response. And so the way this just works, we have our policy. What does our policy do? It acts, which gives it some reward. And then given that reward, we have to update the policy. And then we go again and again and again. That makes sense, I hope. Let's move out of here and let's go back to the computer. And let's talk about how this is possible. That part that I always keep mentioning, let's actually dive into it now. The part of how do we actually update the policy's weights given an external reward. One thing I want to point out, we will be using, or I will be building as base using the reinforce algorithm / paper. It's like a 1992. Let me drag it over here. Implementation algorithm. This paper, you can go and read it. I think it's a very dense paper mathematically. Honestly, you could be kind of left grasping at straws a little bit. It's kind of like, it's tough. But there was actually something, and I'll get into this later when we actually code this up. We're going to be implementing this algorithm into the cart pole example. And from there, this algorithm builds heavily on the modern algorithms that are used in RLHF and in post-training, such as PPO, GRPO, GRPO. I don't know how people say it. I like saying GRPO. So proximal policy optimization and group relative policy optimization. Those two are really big and very important in the modern world of that. And then we will also be going into DPO, which isn't reinforcement learning, it's preference optimization. We'll talk more into that, but we want to build our foundation. This is the algorithm that I saw was good for that. But this, again, as I said, this was a really dense paper. I would say that a good way to go about this is reading this beautiful blog by Lillian Wang. She makes these extremely smart and important blogs that really help me understand how some of these things work. I used her blog on diffusion models a lot to learn diffusion. But here you get kind of a explanation on policy gradients. So just to read over this, the goal of reinforcement learning is to find an optimal behavior strategy for an agent to obtain optimal rewards. We talked about this. But policy gradient is a method that optimizes the policy directly. Now, I didn't go into differentiating what other options there are. I just talked about policy optimization. But there's also value-based optimizations in which we have a value which kind of describes how good a state is to give you rewards in the future. And then policy is what actually generates these rewards. We have this here, I believe. So we have the policy. So we have the state value functions, the expected return of a state. It basically tells you, again, how good a state is to give you a reward. Reinforce is a policy gradient algorithm. And you can read more about this, the proof of the theorem and everything. But if we scroll down, things are put very Englishy for us in this reinforced part, in which we are straight up just told the process on how to use the reinforced algorithm to update our policy parameters. I will go more in depth on this right now, but straight up, this is kind of what it says, what we have here, right? We have that we assume a network N is trained on episode by episode basis, where each episode consists of k time steps during which, and then a reinforcement value is delivered at the end of each episode. Let's talk about what a episode is in reinforcement learning. Actually, let's go straight to coding it, and then we'll learn more of the vocabulary as we go along. So I'm just open up this Colab notebook, and we're gonna start using this thing called OpenAI's Gymnasium. This is kind of where the environment of Cartpole is. All you got to do is import it. Go to any Jupyter notebook. Let me get this stuff off my desk. Okay. All right. So let's go code this up. The way you kind of grasp at the we're going to be using the Cartpole environment. We make an environment and we do gym.make. Oh, look, and it got it for us. So we have Cartpole v1. This basically makes our environment. And then what we have is our observation. And what we have is this function called environment.reset. What this does is it starts the environment from scratch, and what it returns is our obs, what we call obs. It's like the observation of the current state. And we also have info. It kind of gives the information. In this case, it's kind of empty, but actually, I wonder what observation prints out. There you go. So what did I say? Observation is the analysis of the current state. The analysis of the current state in cartpole. Remember, I talked about 4 values. These are the 4 values. Now, given these 4 inputs, we are supposed to make some policy model that outputs the correct action given that observation of the state. The correct action is hard to gauge, right? But an action that gives us and yields higher rewards is basically what we're looking for. Again, as I talked about, if we print the shape of this, it's 4. These are the 4. This is kind of like the information that we have. I'm actually curious. Print this out. It's a NumPy array. So we are going to try to implement this using JAX. And I'll go more on that into like at the end, because another goal of this summer would be not just having a full understanding of the modern post-training pipeline, but also a very holistic view and understanding of JAX and JAX principles. You're going to see this implementation might be a little bit JAX primitive in terms of not fully optimized. That is a goal that we will have throughout the summer to learn to truly optimize JAX code. But that's for the future. Another thing that our environment gives us is our action space. Now, our action space, action space, my bad. What our action space is, here it says discrete too, and I'll go more on that in a second. Our action space tells us the possibility and the range of actions that we have. Basically tells us our output size in a way. In this case, we're given discrete 2 for cartpole v1. What does that mean? Well, as I talked about before, given the observation and the state, we have 2 options. We go left or we go right. Left, right. I don't know how it goes. I don't know how it looks on the camera, but we either go left or we go right. And this is why it's discrete. There's 2 options. There's also continuous. If you could think of like a robot gear, which is like a robotic arm and you want to grab something in real life, that is a very continuous space. There aren't 2 options. There's practically infinite options. In that case, things get a little bit more difficult to train, but the action space would say continuous. And then we give a range, let's say 0 and 1. So it could be like 0.661, 0.391, things like that, right? And I'm going to copy this over, but actually, let's actually verify this, right? Let's see our possible actions. So what we do, let's also understand like the API for this. There is the action space. If we put .n at the end, this gives us just the number, not like in integer form, not like an object like this. And what we want to do is, let's talk about what we need to do given this environment. And also, let me just show you guys what cartpole gymnasium. So you guys have definitely seen this before. You know, it's this. It's literally this, what we do. It literally looks exactly like that. I have some visualization code, but this is basically our goal. And our goal is to keep this as straight as possible without toppling over, all that. But we have to do a couple things, right? We have to initialize a function that outputs an action probability given the state. So that is our policy model, right? So we have to initiate a policy. Because without the action, then there's no way to grade that action. And what we have is that's a function. We'll talk about that more soon. And then let's look at the algorithm. Oh, initialize the policy parameter theta at random. That's our policy. We have a neural network, random weights assigned. How do we train it now? It says here, generate one trajectory on policy. So what that means is, and then 4 times from times 1 to t, we estimate a return, and then we update the policy parameters. I'll talk about what a return is. But in essence, this is basically just telling us, and if you remember here what this told us, assume a net is trained on episode by episode basis, where each episode is case steps. What we want is to loop through n episodes, let's say. Now, what episodes are in reinforcement learning, that is one whole sequence where either the model fails or the time limit runs out. In the case of cart pole, it's 500 time steps where the cart is trying to keep the pole up. If the pole falls, it terminates. If it reaches the end, it also ends. That's 1 total episodes, and we get a reward for each action taken. And then within those n episodes, obviously we want to generate an episode, and we want to calculate the return. We'll get more on that in a second. And from there, we want to update the weights of our policy. It's a very simple algorithm. This is what reinforces. And then the specifics on it, it's these numbers. We'll talk about that. But what is the return? Maybe, let's see. Let's construct this core algorithm, and let's talk about that right after. So let's just kind of pseudocode our way through it. We want to loop through n episodes. Then we'll kind of link it to the API, the actual API. But let's say 4 episode in range. Let's give 1,000 episodes. Right. First thing we want to do is generate an episode. Second thing we want to do is calculate the return. And then third thing we want to do is update weights, as stated. Let's see how this episode generation kind of works. What we want to do is we are given an observation and then the information. The information doesn't really matter. You saw it was empty. So we reset the environment, and then we're going to set, just like it's telling us, we're going to set done equals false. Done just basically tells us if the episode is, again, done or not. And then while not done, so while it's still going, we want to do a couple things. We want to get an action. We want to get an action, and then we want to get the next state, the reward, and then whether it's terminated or truncated, and then the info, but we can leave that. The way we do that is we do a step on the action. Let's pseudocode this part, action. This is basically telling us, okay, the next step in our environment. Here we declare if done is terminated or truncated, it turns it to true. And that's when your episode ends. And we set the state equal to the next state. And yeah, end step basically just makes a step in that environment given the action that you took. Now, how are we going to get this action, right? This action, remember, it's generated by our policy model. So let's build a quick neural network in JAX. So let me, so first import jax.numpy as JNP. And we're going to use the Flax NNX API. So let's just load those in. And let's make our model. Let's call it the policy model. And it passes nnx.module through. And let's initialize this model. Let's just do like one hidden state. Yeah, one hidden layer, and that's it. Size. Okay. Let's just do self dot. The first layer is a linear layer, where the input is the input size, the output is the hidden size, and in JAX, you can't forget this. We have our random number generated key. So let's just have that there. Good practice. FC2, and then let's have a second layer. Here we take the hidden size as input and we pass it along to our output. And yeah, I mean, that's just our model. And let's call our model. And let's just pass the key. I'll make this better in the future, but this is just our original implementation. And here what we do is we just call the ReLU function on the first layer. So we pass through the first layer. Second layer are the logits. Let's call them logits. And so that kind of is just a value, right? And from those two values, this is size of, I don't know, you can imagine this to be like 2.3, 1.7, left or right. And here we're going to decide on an action. We're going to randomly decide one. Historical key and logits. And we're also going to get, very important, we're going to get the log probability. This is going to be important for our loss function later on. And so we have our action, we have our log, our probability. So what we're just going to do is we're just going to return our action, and we're going to return the probability that this action was taken. So let's make that model. And so now you see when we declare the action, we want to, let's see, we have our action. Obviously, we want to initialize our model later, but we get the action and the log probability. And there we just pass to our model. We're going to declare the model later. We just pass our state, or well, in this instance, our observation. And then we're going to be using a subkey. Something really important, we'll talk about this now. In JAX, we generate our key, right? Random.rng key. Let's just do it by episode, right? It's just a random number. This gives us, this allows to reproduce whatever we have. We have to split the key whenever we want to perform some action on it into a subkey. So let's just split the key into two. And you see here, like, we don't have our model initialized. Let's initialize it here. We have our model, let's see, policy model. And what do we want our input size to be? Remember, our input size, we want it to be 2. In this case, yeah, let's just kind of follow it through like that. And here, let's just RNGs. Let's just use 42. I like 42. And then we also want, forgot to import optax. This is for our loss. Here we have our optimizer. Let's just use Atom. So we pass our model. Here we ask for the learning rate, and with respect to the parameters of our policy model. Should run fine. And yeah, so now this model, what we pass is a JAX numpy array of the observation of our state in our current environment, and the subkey to our model. Then what happens is input of, this is the input, right? We pass it, and then the output is of size n, whatever. This is our action and our log probabilities. And that's it. What we just did was this loop where we do one episode of a cart just moving back and forth. Each action, I can't tell you specifically. I think might be each time step, so maybe 500. I'm not too sure. Should be actually, yes. Every time step. So let's say at time 0, we're given this position. At time 300, we're given at time 300, yeah, we're given this position. The thing is like this. Our inputs are different. We have to generate an action. We generate 500 actions, or whenever we fail. And this loop takes care of that, right? So we generate an action, and given that action, we convert this into an integer. Given that action that we take, we move the environment towards that. Obviously, this gives us a reward. This is one of the more important things. Gives us a reward. Then we also want to update to the next state, and we also want to update the done. And now we want to calculate the return. The return is the G. Now, one more thing. Well, let's do returns. Returns will be an array, and let's initialize G to 0. And we have this hyperparameter called gamma. So what the G does is it kind of estimates how, like, given the current state and the current time step that I'm in, how much reward did I get from here on outward? And what the gamma does is it kind of depreciates that value over time. For example, the action that you took right now that gave you the reward in the following step does not necessarily mean that, 50 time steps down the line, that action was the best one, if that makes sense. Gamma tries to take this into account. And it's basically just a recursive formula. It's a simple recursive formula, but we're going to need to keep track of our rewards and other things as well, but mostly our rewards. And so let's make an array called episode data. And episode data, here, episode data, we're going to append, I'm just going to append the reward. You can append other stuff, and I did, and I'll show you guys in the repo. But for now, let's just append the reward, because we want, for every reward in the reversed episode data, right? So we want to start at the end. What we want to do is update G by this, just like that. And then we're going to return, append this G. And then let's just like reverse it. I'll explain this now. So remember, so what we're doing here is we're starting from the very last reward. The reward is, start from the very last reward. So at time step 500, what was the reward for 499? And we add this to our G. First, remember, it's an estimated value of the total reward kind of thing. So in a way, let's just see, this kind of turns into reward plus G, right? So at time step 500, we had a reward of 1. Then at 2, or at 499, we had 0, so we kind of failed. And then from there on, we kind of build this accumulative reward. And we depreciate the value over time with the gamma. That was the whole point of this. This is just recursive, right? And then we just append it. Now, remember, this list is backwards. So we just go from there. The reason we start reverse, the reason we start from the back end is we want to see the actual results of what we did. If we start from the front, we're counting the results, we're counting the rewards without knowing like the ultimate, like how we ended up. So we want to know where we ended up, and then from there, think about it kind of as retracing the steps of how you got there. And if the steps that you took were good enough for that, basically. So yeah, we want to bring this number up. And this is a very important list to have here, what we call the returns, because this is what lets us update our weights. And so let's make a loss function now. Now we have some value, right? Some estimated value of the actions that we took and the space that we were in. And let's update those weights. So let's make a loss function. Def loss function, right? So let's take our model, our episode data, and our returns. And now here we're actually going to have to add a little bit more to the like episode data, because we want our reward, obviously. But let's make it a tuple, right? Let's get our reward, and let's also get the log probability that we displayed here. This kind of changes the way we're gonna go about this. Let's just cover it up. Perfect. What's the issue? Is this on the outside? Yeah, I'll figure that out later. Yeah, whatever. It's because this hasn't ended here. So our loss function, we want two things. We want the log probability of our like model output. This probability tells us, or not two, sorry, one. This probability tells us how much the model wanted to do that specific action. And then we want, at that time step, we want to see the returns. Remember, this is an array? Yeah. And so what we did here, basically, we got all of the log probabilities. We made it into a NumPy array, or a JAX NumPy array. We did the same with the returns. And then we want the average of the returns and the log probabilities. And we will return this loss here. This is the same exact thing as this, right? We have this probability of an action given a certain state. We have our G, which is our returns. This is the little gamma. This is our learning rate, and then we add it to the original parameters. That's kind of its own version of backpropagation. Here we have our learning rate, and we return the loss here. Now, actually, there is a little bit more nuance here. We have to normalize the returns. This is a math trick. Reason being, for example, let's say the return at a certain state is just super high, like 300. That's really going to mess with the gradients of our model. So we want to normalize it. Yeah, I mean, it did it for us, but we just normalize this. We add this little value so that we never divide by 0 in any case. And this is our loss function. And remember, wait, this is really important. This is negative. Why is this negative? Remember that our goal is to get the returns as high as possible. But our goal in a neural network is to get the loss as low as possible. The way you can think about reinforcement learning is that we get the reward. We want to maximize whatever value we get in the rewards. And you can think about the loss as a translation of that for our policy model. So again, the goal of the policy model is literally flip-flopped from the goal of the reward or the output of the reward. We want to raise the reward as much as possible. But how do we speak that language in a way that a neural network understands? We know that that is by reducing the loss. And thus, this is, here we have this negative return here. And yeah, I mean, here we pretty much update the weights, right? We have grads. Let's get the gradients of given our loss function. And we pass our model, episode data, and our returns. And then let's update our model given the gradients that we obtained. And that's pretty much that. I want to kind of show you guys. This should work if you run it. Now, there's no printing, obviously, but this kind of gets to the nitty-gritty on how this algorithm functions and kind of how this whole process is of reinforcement learning. In a way, is we have all this noisy data, self-generated data, very noisy, but we have some function that raises what we call a reward, and then we want to translate that in a way our neural network understands so that it can update its weights. Hope the normalization made sense, because otherwise the gradients would just be all over the place, either approaching 0 or approaching, up there. And I'm gonna copy and paste some code here, and this code basically is it's the same thing. I made some changes as I was like making some let's say I was optimizing my own, and I was updating my own weights for my understanding of JAX. This code right here is honestly very inefficient, and I'll get into it a little bit now. But this is a little bit more updated, more rigorous in the JAX step. Like, for example, this whole final step that we did here, if we wrap this in JIT, which stands for just-in-time compilation, we just unroll that, and it is a lot more efficient for XLA, accelerated linear algebra compilation. Crazy. But yeah, pretty much for XLA compiling. And see any changes, pretty much the same stuff here. I added some kind of visuals here, so I'll kind of push those through. And I did a little bit of an update to the policy model. I'll get into that now. I basically separated the call from the actual sampling. This is important for V mapping, which is like mapping vertically, like per batch. Truth be told, I am still grasping these concepts, so I will get into explaining it more in the future as I get more accustomed to the JAX environment. And also, bro, let's talk about this. This whole time we were working in Gymnasium, but Google Brax is a thing, and that is basically a JAX optimized environment for reinforcement learning. I'm gonna keep that in mind for the future. But yeah, we have this here. I think, do I have any more code to generate? No. So I'm gonna run this, and we're gonna talk about the results now. So I'll be back soon. Okay, so I let it run for a little bit, and here you can see total reward 500. Now, what we're measuring as total reward, let's see where I can show you it. It's just the sum of all the rewards, right? So if you think about it, 500 is literally the max. So we had a perfect run, and I have some charts right here. One thing you have to keep in mind is that reward modeling is very noisy. It's like up and down, up and down, up and down. Because each situation, each state is very different from the previous one and from the next one. Each episode is very different. We're not looking at clean data whatsoever. So what we want to measure mostly is the trend. Now, the trend, I'm a little disappointed because it dipped, but the trend is upwards, right? And I also recorded this little GIF for y'all. So you see how it's balancing it, right? It's not falling over. I'd love to see the first one. Yeah, I kind of just fell over. I guess they stop it at a certain angle. Didn't record no more. But yeah, I mean, this is just kind of showing that our model is generalizing and learning it. Look at it go. Look at it go. Damn. Yeah. So pretty cool. Pretty cool. Now, one thing I want to note, let's actually tear apart my implementation. Very inefficient. One thing that I'm getting more used to understanding is that philosophically, when you are working with JAX, it is smart to avoid loops, Pythonic loops. Reason being that we need something that can be traced so that XLA can compile it. Now, Python loops, they're not like JAX primitives. You have to use these JAX primitives. There's a lax.scan, there's vmap. Try to use vmap here. I don't think I used it correctly, so I'm gonna have to go back to the drawing board, figure that stuff out. But for example, this while loop right here, not needed. It could be so much more efficient. It could be so much more efficient with jax.lax.scan, which I've only used a couple times before, so we're gonna have to look into that. Maybe even this for loop right here, because this is recursive. Yeah, different things like that. So one of the things I'm most excited for this summer is to actually witness that growth and see how much I improve working with JAX. But pretty much that is it. I'm gonna show you guys this repo. This repository is where most of the work will be going into for understanding this reasoning. So here we have the reinforced folder. I'm going to add a visualizations.py, but you know, here we have our policy model. Here we have our implementation of the training, right? So we have our loss function, we have our main training loop, which shouldn't be so loopy. And yeah, I'll write up a little README after today, but hope you guys enjoyed. Hope you guys got something out of it. Next week, we will be touching on another topic and slowly build our way towards implementing PPO for LLMs and beyond. So thank you guys so much for watching.